All right, so hopefully just take not too much of your time to go through and make a review video, but this is your review sheet and I've actually made a few changes. And so there's something called Unit 1 Review Revised sheet that you should print up or else just catch the changes here. Now I have 2 asterisks next to a few things, like for instance rounding numbers to significant figures. The 2 asterisks means that I don't think we covered it in lecture, and that means it'll be on your test, there'll be a question, but it will be an extra credit question. Get extra credit. By the way, I will talk about rounding numbers just briefly in this review video. So we have a couple of asterisks next to the moon. Your weight on the moon will be less, but I don't think I said in my notes this semester it's 1/6. Your mass will be the same on both the moon and the earth, but your weight will be 1/6 on the moon as the earth because of the difference in gravity. Weightlessness is free falling. Be a question on there. It'd be worth extra credit. And also here on your review sheet, I don't think we did a problem in my notes. I couldn't see where we used Newton's second law, F is equal to ma, and did some calculations. So I'm going to delete that as those will not be on the test. Yay, right? Scrolling on down, I've got, again, problem given wavelength and frequency, calculate speed, worth extra credit. Hey, can't beat that. And I am going to add a problem. So where it says given frequency and velocity, calculate wavelength. So AA means it's added, so for normal credit. So if you want to print this off, it's available on Canvas. All right, this is also available on Canvas, so I'm going to kind of step through this, what I call my review PowerPoint slides. And so it's broken out into the 4 parts. You'll have a question, and again, I probably won't spend a whole lot of time on this, but you'll have a question about the branches of science. Wonder if my finger will, oh, yep. That works. Okay, so of course we are kind of down here, okay, and we are going to talk this semester about generally physical sciences. So you have a question about that. You'll have a question about the scientific method. There's different ways of kind of looking at it, but they have some key terms like observations, hypothesis, experiment, and then actually we kind of get in a loop, this loop right here, where we kind of experiment, assess, experiment, assess, and then if some point our hypothesis keeps being reinforced, it can be what I call king to a theory. So those are some kind of main terms in what we call the scientific method. Here's one for you. We talked about worldwide we have these basic units of measurement. So generally know mass is a good one, length is a good one, temperature, those probably these right here. What is the basic unit of measurement with internationally speaking? Let's see. I said that you're supposed to know 3 prefixes. Kilo means 1,000 times. Centi means 1/100th. Milli means 1/1000th. And I said micro means 1/1,000,000th, 10 to the -6th. So know that and know kind of the symbol for each of them. Looks like I have a typo here. I didn't do it, but the symbol for micro is the Greek letter mu. It kind of looks like a U with an extra tail. Sorry about that. Okay, so rounding the significant figures. Like I said, I'm not sure I talked about it in my notes this time, but I did mention it, I think, on one of the evenings. So for instance, if I have 5.63 times 2.1, okay, I don't have my calculator handy, but rounding it to significant figures means whatever my answer is, I need to truncate it to 2 digits. I have 2 there and I have 3 here. Okay, so I'm only allowed 2 digits there, and it's kind of tricky. So for instance, if I had if I had 4 times 6.3972, okay, how many significant figures would I be allowed? And how would I have to round to? Well, if I have 1 significant figure here and I have 5 here, you always have to be conservative. You have to go with the fewest. So it would be 1. All right, on to the next part. So I'm looking on my sheet here for part 2, chapter 2. You're going to need to know the terms speed, velocity, and acceleration. So of course, to get speed, we just take the distance and we divide it by the time. We can actually then use it as a, let's see, I have down here no problems. Given distance and time, calculate speed. Given time and acceleration. So yeah, that's not it. We're not going to do, I don't think you have an example like that. So speed versus velocity, though, you'll probably have a multiple choice question about this, or a vocab. I'm not sure. The difference is that speed just says how fast, and velocity is how fast and also direction. So velocity gives direction. So we'll have some examples here. If you only say how fast a car is going, it's speed. If you say how fast going and the direction, that's velocity. And we can use these little arrows to show velocity. Works quite well. Then the other one is acceleration. So acceleration is a change in velocity. And since velocity has two components, you're talking about speed or the direction or direction. Okay, so these are all examples of acceleration. Okay, so changing speed and or changing direction. We can calculate acceleration. Let's see, given time. We calculate acceleration by taking the difference in the velocities, the final velocity minus the initial velocity, divided by the time over which that change in velocity occurred. Okay, these letters, this Greek letter looks like a triangle called delta. So that's delta V, or change in velocity, divided by delta T, change in time. All right. Let's see. Falling objects accelerate 9.8 meters. They go 9.8 meters per second faster for every second they fall. And so here's Galileo, maybe, leaning over the Tower of Pisa, and he's dropping two objects, and these two objects have different masses, but they are actually accelerating with the same acceleration. So G is that 9.8 meters per second, or 9.8 meters per second squared. That's acceleration. We've watched a video where on the moon, the astronaut dropped a falcon feather and a hammer, and they both landed at the same time, because in absence of air resistance, things will definitely naturally fall at the same rate, whether it's on the moon or the earth. We don't have any air, but that would be a bad thing. This is actually showing you a ball falling faster and faster. So here it is 1 second, it's falling at 9.8 meters per second. We give it another second and it's 2 times 9.8. We get another second and it's 3 times 9.8. Another second and it's 4 times 9.8. Okay. All right. So this is actually how would you calculate the speed. Okay. Speed is what you think it is. Speed is actually what we say, distance divided by time. So in this case, we could go distance. So that's 80 meters divided by time, which is 4 seconds. All right. Acceleration, let's see, I've got my notes here. I say, given distance and time, calculate speed. That we just did that. Given time and acceleration, calculate final velocity. So you're going to have an equation sheet, and I'm not sure. I'll give you a copy of the equation sheet that I gave you the other day. Now, if your initial velocity is 0, okay, then this equation becomes this equation, where you can calculate how fast you're going to be going at any time t. If we take t and we multiply it by the acceleration that's the object is undergoing. So we can actually apply this for something that's dropping. So something that's dropping, obviously, the initial velocity is 0. And notice this, the A here is going to be 9.8 meters per second per second, or per second squared. In this case, the time we're going to let it fall is 5.2 seconds. So then we're going to plug that in there, 5.2 seconds. And we're going to get the final velocity. So you will see a problem kind of like this on the test. Now, I need to see all your work. So my final velocity is equal to 9.8 meters per second squared. And I'll try to remind you this, but if you don't do this, then you won't get all the credit. 5.2 seconds. Now the cool thing about this is one of these, that seconds will cancel with one of these seconds, and you'll have units of meters per second. We talked about rounding. You're looking like you have 2 digits in both of these, so you actually should only round your answer to 2 digits. So I hope that works for you. All right, on to still in part 2, but chapter 3. So you're going to need to, or want to know a little bit about Newton's 3 laws. Newton's first law is that an object at rest will stay at rest unless acted upon by an outside force, and also an object that's in motion will stay in motion unless acted upon by an outside force. Of course, this deal up here, we're going to kind of call that inertia, in that if you quickly pull that piece of paper, this is going to stay there because it's like at rest and it wants to stay at rest. So anyway, so that's Newton's first law. Newton's second law is force is equal to mass times acceleration. So I kind of like to say that you apply a force, an object has a certain mass, and then you will actually, because that force applies, see this acceleration. So this is where actually you're going to have some problems for extra credit. So that would mean the greater the force, the greater the acceleration. Okay, Newton's third law says that for every action there will be an opposite and equal reaction. So you can see this person pushing with a force of 100 newtons on the wall, and the wall is pushing with a force back of 100 newtons. Okay. All right, for every action there is an opposite and equal reaction. An equal and opposite reaction, yeah. Newton's first law is that an object at rest will, an object either in motion at rest will want to remain in its current situation. So for instance, this person is standing as the bus moves. He didn't get the memo, so the bus moves and he's caught off guard. Here he's moving with the bus. When the bus stops, he's still moving. So anyway, inertia. Gotta love it. Gotta love it. Okay. Let's see, looking at my notes. Mass versus weight. Okay. So mass is kind of related to how much matter is in an object, and weight is a response to gravity, basically. Okay, so we actually have a little formula to calculate weight. Weight of an object, whether you're on the moon or the earth, is equal to the mass of that object times the gravitational force, or the acceleration due to gravity that object is feeling. So weight is mass times the acceleration due to gravity, which is different if you're on the moon or on the earth. Okay, so here we go. Weight is force. So weight is equal to mass times gravity. This actually is Newton's force of gravity right there. Yep. So here's the example of if you were on the moon. Notice that your mass is 100 kilograms. Sorry, if you're on the Earth. If you're on the Earth, your mass is 100 kilograms. If you're on the moon, your mass is also 100 kilograms. But with regard to weight, because of gravity, on Earth you would weigh 980 newtons, and on the moon you would weigh about 1/6 of that. 162.2 newtons, and that is actually one of your extra credit points, that there's a factor of 1/6 between your weight will be 1/6 on the moon as it was on Earth. All right, on to part 3. So part 3 I have in my notes that we talked about work. Definition of work, and there's different ways. Work is accomplishing something. One way is if you're pushing with a force an object a certain distance, you can calculate the work that you expended, like this. So we know we could measure the force of this guy is expending, and the distance over which he relocates that box, that's work. Okay. All right, notice that this person, it's kind of silly, he's pushing a brick wall, and the brick wall is not going to move, so D is 0. Okay, so force times 0 is not accomplishing any work. Poor guy. Units of work are same as units of energy, which are the joules. And you could break the joule down into kilogram meters squared per second squared. We could also break it down into Newton meters. So power is related to work this way. So power is work divided by time. And you guys did some of that in lab this semester. Units of power are watts. Don't blame me, it drives me nuts. Okay, that's another W. A watt can be broken down into joules per second or kilogram meters squared per second cubed. So we have this deal with, and I have it on there's going to be a question on your test about potential energy versus kinetic energy. So potential is stored energy. Kinetic energy is energy generally associated with motion. And we kind of talked about energy and work are related. Like a few slides ago, the work accomplished is equal to the energy spent by that person. So actually, the units of energy are the same as the units of work, joules. All right, have in my notes, problem, given mass and velocity, calculate kinetic energy. That's coming up. This must be the pendulum one. I also have in my notes, just generally probably be a multiple choice question, but with this pendulum here, you would say actually here V is equal to 0, so this velocity is equal to 0, so basically KE is equal to 0, right? Because kinetic energy is an energy associated with motion. But it has a significant height, which means it has potential to fall. So that means it has lots of potential energy. Okay, and then down here it has a lot of motion. So I'll put KE is high, and basically the H is 0, so PE is equal to 0. Sorry, it's really messy, but hopefully you heard me say that. So yeah, there will be a problem where you'll need to calculate the kinetic energy of an object, and you'll have this formula. So it's kind of plug and chug. So if we take this one right here, KE is equal to 1/2 times the mass, which is 7 kilograms, times the velocity squared. So that's 13 meters per second. We have to square that quantity. So don't forget to write down all your numbers. And actually, as we round it, there's one digit here, 1 sig fig here, and 2 sig figs here. So go ahead and give me 2 if you want, but you're only justified really 1. All right. Yep, and I have in my notes, you need to be able to, given force and distance, calculate force, distance, and time, calculate power. So remember that power is work divided by time, and here work actually is force, which is 4.5 newtons, times distance. So to me, what I got is power is equal to 4.5 newtons times 0.343 meters divided by the time, which is 34 seconds. And then remember that the units are going to be in units of watts. So that's kind of how that works. All right, now on to part 4, about waves. So there are 2 types of waves. We kind of start with the transverse waves. Remember that transverse waves an example of transverse waves are light. And we said actually light is just one cousin of a bunch of energies we call electromagnetic radiation. So waves have this crest, and they have a trough, and they have a wavelength. Now here, remember that for wavelength we use the symbol lambda, so that's wavelength. All right, so I think so. And then the other type of wave is called a longitudinal wave. Let's see if I see the word longitudinal. There we go, longitudinal wave. This is the slinky type. An example of this is sound. So here we can see the, you still have a repeating unit. So this we have compression where it squishes together, and rarefaction, not fraction, rarefaction where it's spread apart. So for instance, then we could go from compression to get our wavelength. Cool. So just to kind of make sure we're on the same page, here we have the longitudinal and transverse. Okay. Very good. There's one more important thing about waves, and that's the frequency. And I said if you were a person standing here, basically you are counting waves as they pass. Okay, so you get your timer, and you get your timer T is equal to 1 second, and however many pass in that second, that's the frequency. So you could have 450 cycles per second. Okay, we actually then call that 450 hertz, same thing. Hertz and per second are the same thing. All right? Okay. So the wavelength and the frequency actually multiplied together will give you velocity. And if wavelength is in meters and frequency is in per second, notice that if you take meters per second, meters times per second, you get units of meters per second, which is a great velocity unit. We can kind of rearrange this. If we divide both sides by frequency, we get wavelength is equal to velocity over frequency. And then if we divide both sides by wavelength, we get frequency is equal to velocity divided by wavelength. So these all mean the same thing, but I'm pretty sure on your test I'm only going to give you that one. All right, so different forms of electromagnetic radiation. So there'll be, I promise, some sort of question about the order of these cousins, these 7 cousins. The most energetic form of electromagnetic radiation is gamma rays, then we go X-rays, ultraviolet, visible, infrared, microwaves, and radio waves. And then in the visible, remember that's Roy G. Biv. So we have Roy G. Biv, okay? So remember I stands for indigo. All right. So then remember that we said that this is most energetic, and actually as it turns out it has the shortest wavelength and the highest frequency. And this one has the longest wavelength, and it has the lowest frequency, and that's not an accident. So one of the things about all of those cousins is that they travel at about, and I don't know if you want to remember, you can make a note card, so you might want to get this on your note card. They travel at about 300 million meters per second, but that's assuming that it's traveling through a vacuum. Now, if it travels through anything else, here's some different types of medium that light travels through, it travels slower. And this actually, refractive index of refraction tells you how much slower. So the higher the index of refraction, the more slowly it travels. And actually that's kind of what gives light dances in our diamonds. Because it travels so slowly. It's refracted a lot. Okay. Let's see. All right, I think we're doing okay. Range for audible sounds. So I like this one with the dogs, right? So remember, sound is a type of longitudinal wave, but its frequency that we can hear is generally from 20 hertz to 20 kHz. And of course, what does K stand for? Kilo. So if I were to unpack that 20 kilohertz, you're talking about this many hertz. Okay, so 20 kZs, KHZs is equal to that, 20,000 hertz. So anyway, those are the audible frequencies. So I guess I would say if something is got a frequency that's higher than audible, we call that ultrasonic. Lower, infrasonic. I think that would do it. Okay, we're getting down to the end. The Doppler effect. As an object is, we have this car that's moving. If you're over here, can you kind of see where the waves are kind of squished together? That's what we call a blue shift. Okay, and actually you're going to see the pitch go up. If you are over here, actually the wavelengths are going to be kind of longer. We call that the red shift. And your pitch is going to go down. So pitch would be higher here, and pitch would be lower here. That's the Doppler effect, and it works with basically you have, in this case, a car that is moving and emitting a sound. Or if you could have a car or something that's moving and emitting some sort of energy. Okay, so problems. I've got given wavelength and frequency, calculate speed. Okay, so like I said, you might only have this thing where velocity is equal to wavelength times frequency, and you have to kind of rearrange that. So what is the frequency? So remember how this works. If I want to get frequency by itself, I can divide both sides by wavelength. Okay, so frequency is equal to velocity over wavelength. So I'm going to take this velocity, 344 meters per second, and I'm going to divide it by that wavelength, 0.55 meters. And notice my meters will cancel. I have units of per second, which is great. Looks like I should round to only 2 sig figs, or 2 digits, because of my 0.55. All right. Calculate speed. I wonder if I added 1. I think I did add 1. Okay. All right. All right, so I think that's all I have. Let me know if you have questions. That's what I'm here for.